Hello. In this chapter, we're going to continue on talking about hypothesis testing, and we're going to go over some important conceptual information that, once you understand the formula, you don't really need to memorize that conceptual information. It should become more automatic for you. So first, we're going to talk about factors that influence significance, what we just determine in that final step when we make our decision. What determines whether or not we reject the null hypothesis. So let's think about it. First, we state our hypothesis. Then we set our criteria, that alpha level. And that alpha level gives us a critical z-score. Then we calculate. And what are we calculating? A z-score. So it's this z-score, both the critical z-score that we have here. This critical z-score marks the boundaries for our critical region, and here we're a two-tailed test, so we have two critical regions. And then we have our calculated z-score, and we're looking to see if our calculated z-score falls here in this critical region or here in the middle. And we're going to reject the null hypothesis if it falls into these critical regions beyond these boundaries set by our alpha level. So let's think about what's going to affect that z-score. So that means what's going to affect whether or not our decision, whether or not we find significance or not, whether or not we reject that null hypothesis. So let's look at our formula here. This is the formula that we have, and we're going to break it down in the next couple of slides. So thinking about what's going to affect the z-score. This is our formula. And we're going to look at the numerator first. So what does this numerator mean? We've talked about this before. So this numerator means the distance from the mean. So we have our population mean, and this could be our distribution of sample means, and then we have another value. And what this numerator is showing you is how far this sample mean is from that population mean. What's the distance from the mean? So the bigger that distance is, the bigger this z-score is going to be. So the size of the difference between the sample mean and the original population mean is going to affect the z-score. The larger this difference is, because that's going to give us a bigger number up here on top, the larger our z-score is going to be. So larger discrepancies, larger z-scores. Next, let's look at our denominator. So what's going to affect the denominator here? We see standard error. Now thinking back to chapter 7, we said that this is a measure of how much distance is expected on average between the mean, sample mean, and the population mean. So this is the expected. This is what the error that we expect to happen. So the variability of scores is going to affect the z-score. So the bigger the variability, the larger the standard error. And also, if you think about the formula and relationships, the numerator relationship to the denominator, the numerator is giving you the measured difference between the sample mean and the population mean, and it's comparing it to this expected difference. The bigger this comparison is, so the bigger this ratio ends up being, the more likely your treatment had an effect and you'll reject your null hypothesis. So if your measured difference is significantly bigger than your expected difference, you're going to get a big z-score and be more likely to reject the null hypothesis. So now let's take a look at the denominator a little bit more detail. What affects standard error? So here I've shown you the standard error formula. And we see here, besides variability, the size of our sample is going to affect. So the bigger this n is, even though it's a square root, the bigger this n is, the smaller our expected error is going to be. So the number of scores in the sample is also going to affect our z-score. The larger the sample size, the smaller the standard error, because the larger this denominator is, the smaller this number is going to be. So again, if you understand the parts of the formula and you understand mathematically what happens, it helps you to understand conceptually what's going to influence that z-score without having to memorize it. So now we're going to talk about the assumptions we make for hypothesis tests with z-scores. And anytime you do a statistical test, there are assumptions that are being made, and if those assumptions aren't true, then the statistical test is not accurate. So the first one is random sampling. The idea is that random sampling was used, and that makes the population representative. The second is this idea of independent observation, which is that all subjects have an equal probability of being selected. We also assume that standard deviation is not changed by the treatment. And so you saw that in one of the earlier videos when we were talking about, I think it was the first video, and I showed you that diagram. And the idea is that everybody's scores are going to be affected about the same by the treatment. So your standard error doesn't vary or doesn't change. Your variance doesn't change. And the final is that the sampling distribution is normally distributed. And so again, that's important because we're talking about these two tails that have the same proportion, and if our sampling distribution isn't normally distributed, those tails wouldn't have the same proportion in them.